Hi, my name is Sodano and I will present you this course on control theory. Today we start with our very first lecture, which is basics of theory of dynamic systems. So to start with it, we have to define what a dynamic system is, and we want to start with a bit of motivation behind this. So the thing is that everything around us is a system, from very simple things such as a heater or a bicycle to very complex systems such as a power plant or a robot, which you might be interested in if you're taking this course. Everything is a system. So from a more formal point of view, what is a system? Well, a system is an object, a device, or a phenomenon, whatever it is, which is synthesized as an aggregation or interconnection of parts. And we're interested as engineers to know how this interconnection of things work. And specifically, in the context of automation engineering, which studies dynamical systems, we want to know how does the system evolve. So we define a system, but what does it mean to evolve? What's this evolution? Well, evolve means to study how a sequence of events happen in an autonomous way. So without human intervention, without someone actively triggering something, but how is this system doing by itself? So we have now two keywords already for automation engineering. One is system, which is this aggregation of parts, and one is the evolution, which is some internal variables of the system are varying over time, and they do not need human intervention to do it. Now, automation engineering in general is composed of three parts. So there's analysis, synthesis, and identification. And we will deal with some of these during the course. So let's define them. So analysis, we have a system. Imagine, for example, the power plant that I showed before. And so you know the power plant and you are feeding something to the power plant. You're giving a certain amount of, I don't know, energy or chemicals or whatever. And you want to know what is the output of it. So what does the power plant give me back in return? And this is the synthesis, the analysis, sorry. The synthesis, on the other hand, is something kind of the other way. So we have the system again, the power plant, and we want a desired output. We have a goal. We want to have a certain amount of energy or a certain amount of chemicals or whatever it is. Okay, what input should I feed to the system in order to have this specific output? And then we have system identification. System identification is I'm feeding an input to something that gives me a certain output. What's happening in here? What is this black box? How can we mathematically describe it in order to understand what's going on in here? This is system identification. Now, in our course, which is focused on control engineering, we will focus mostly on analysis and synthesis. So the system identification will not really be part of the course. So let's start now with the actual content of the course. And let's start with the dynamical system. Because as I said, this lecture is an introduction to dynamical systems. So we have to define them. And a dynamical system is defined as an oriented system which evolves over time, which we can represent like this. There's something you've already seen, so this input to the system, output to the system, and there's something more. But before defining all these variables, there's one word which is very important here, which I haven't mentioned what it is, which is oriented. So I talked about systems, but I didn't say what an oriented system is. Well, an oriented system is just a system that has a cause to effect relations between its variables. So there are some causes, the input in our case, that cause some effects, which are the output in our case. Then we have other variables. One is the state. It's a very important variable. It's called internal variables as well. And basically is a set of physical quantities, the specification of which completely determines the inner state, the evolution of the system and the inner status, the inner state of the system. This is the state, x, which is usually indicated by x. Then we have, as already specified, input, which are these causes and are also called independent variables, and the output, which are the effects, also called dependent variables. And then we have something else. This is a disturbance that acts on a system and is something that is unplanned is something that is not applied by someone, by some device which we want that applies something to it. It's just something disturbing the system. So you can imagine that, for example, if you have, I don't know, a simple case could be a pencil standing on a table. This is a system. If no one is touching it, the system has no input. And there's also, the output is just that the system is still. But then there could be a disturbance that disturbs the state of the system, which is a blow of wind, and then the pencil falls down. So this blow of wind that disturbs the state of the system, causing a change of state, is the disturbance. This is a very intuitive way to understand what a disturbance is. Now, let's go on the math for it. So a dynamical model of a dynamical system is something like this. So we have the evolution of the state, x dot, over time. T is the time variable, which is a function of state and the input. And then also the output variable, whatever it is, it can be part of the state, it can be something else. This doesn't matter. It's also a function of the state and the input. And the function could be different because they technically have no relation. So in this notation, and also for all the rest of the slides, we're not using bold notation for vectors because it would make it very, very heavy. But you have to imagine that everything here, but the time, could technically be a vector. So everything could be bold in theory. Time is just a scalar, so the t is not bold. So we're dealing with things that evolved in time. We know it. We just get rid of t, again, for simplicity of notation, for having things a bit clearer, a bit lighter, so there's no t in the notation. And this is called the state space representation of the system. So it represents the system in state space because it's all centered around the states. It's all dependent on the state. We also want to give a further simplification of this system that we're talking about, and specifically about the functions f and g. What do I mean? I mean that we want to deal with something that is linear. And so now you see that both the state equation and the output equation are linear. And also that these matrices here, A, B, C, D, do not depend on time. So those are matrices. X and U depend on time, but the matrices don't. And this is why it's called time invariant. So the systems has some constants which are described by the matrices that do not depend on time. From this system, we can define some nomenclature, some important properties and important names that you should know about it, because there will be some recurring concepts in the future. One is the free evolution or zero input response. Imagine you have a system and no one is disturbing it. No one is actively putting an input on it. So this part disappears because u is 0. This part also disappears. And this is how the system evolves. And it means that there are still some constants that evolve based on the state. And then we have how does the state vary based on what's going on, based on the initial state, based on the internal evolution of the system, without any input applied. And then we have the zero state response, which is the forced evolution. So the state is 0. We don't have any state, but there's an input applied to it. How does the state evolve? And this is something you can understand intuitively by thinking, for example, about the pendulum. A pendulum is just in the vertical position, so the state is 0. And then there's someone, so this part disappears, and then there's someone that just touches it and the pendulum starts swinging. Well, this is a forced evolution because there's no state and there's an input applied to the pendulum that causes a change of state, and we want to study that change of state. So, back to a bit of nomenclature. This then is the matrices that define the dynamical system, A, B, C, D, and they are relations between the state and its own evolution, so the dynamic matrix, or the state and the input, state and output, input, output, and just matrices. So, problem setting. We have these equations that are the evolution of the state and the evolution of the output. And we said that we want to deal with something that is linear, because in this course we will mostly see linear stuff. Something is time invariant because we don't want these matrices to depend on time, and on something that is continuous time. So we are working with continuous time, not with discrete time. Discrete time systems and digital systems in general will be a topic of the course later on, but for now all the lectures are about continuous time systems. Let's do a very quick example just to understand a bit the idea behind it. So we have a mass, and this mass is sliding on a surface, and there's a force applied to it. So the physical model comes from, again, physics, and then it's force equal to mass per acceleration. So if there's the case of no friction, and we have that the acceleration is equal to the derivative of the velocity. Now imagine the case in which there's no force. This term goes to zero, so we will have no force. Mass cannot be zero because the mass is different from zero. So we will have that velocity is equal to zero. So the derivative of the velocity is equal to zero. So basically the velocity does not change from the initial velocity. And this is something that is told in the Newton's first law. So if there's no force applied to the mass keeps sliding or stays still, depending on whatever is doing before. This is exactly what it is. We can solve the differential equation that we have in that we started with. So we just integrated, we get the solution, and with this solution we can also infer some interesting properties of these systems, of this dynamical system. For example, what if we double the force? So we have a certain force applied here. What if it's doubled? Well, it's just twice what we had before. The velocity is just twice what we had before with half the force. Because linear combination of causes implies linear combination of effects. So we have this superposition principle which holds for linear systems, which is very important. It's something that we'll carry on for the whole course. Now we have some definitions about the system, about nomenclature, and also how to write a system, but that's not enough. We want to know something more about the system. So we want to know a property which is called stability, which is, for example, if you go back at the examples that are shown at the very beginning, you have a bicycle, you want it to be stable, you don't want to fall down. You have a robot, for example, a legged robot, you want it to be stable, you don't want it to collapse at every step it takes. So we want to study the stability of the system. To do it, we consider the system in free evolution. So at the moment we are forgetting about the input part. It doesn't matter. What is the concept of stability for this system? So what does it mean to be stable? Well, we want to study how the system evolves based on perturbation of the initial state. So we have the system in this free evolution, we have an initial state, the system would evolve. But then what if we perturb the initial state a tiny bit? What happens? And intuitively, you can imagine that a system is stable if a small perturbation causes a small evolution, a small variation of the state, while it's unstable if there's a big variation instead. So back to the examples that I mentioned before, if we have the pencil standing on a table, if we give a small perturbation to it, it falls down. So the system is probably unstable. But then if we have a pendulum, on the other hand, and we perturb it a tiny bit, the pendulum will oscillate for a bit and then it will keep still and go back to the position that it started from. So it's probably stable. So this is the intuition somehow behind the stability theory. To define this, we have to define an important concept, which is the concept of equilibria. So an equilibrium is a state, and specifically a state is an equilibrium of a system if it causes a degenerate trajectory. What does it mean to cause a degenerate trajectory? Well, this is the equation that defines it, and basically it says that if we start from an equilibrium, the evolution stays in the equilibrium state. So it says that basically the evolution, the f that we define at the beginning, is 0, which in our case we're dealing with linear systems. So this is 0, this is our f. So basically it's saying if a state is in equilibrium, does not evolve. Nothing happens. Equilibrium means the evolution is just 0. There's no variation in the state quantities. The fact that it does not evolve, however, doesn't mean that the system is stable. And you can really understand this thinking about the pencil. The pencil that is in the vertical direction, like balanced on the table, does not evolve, so it's in equilibrium. But it's not stable because we said if we touch it a tiny, tiny bit, so we perturb this initial state for a bit, the pencil falls down. So this is the idea, to grasp the idea behind the definition of equilibrium. So equilibrium is not enough. We need to know whether an equilibrium is stable or not. To do it, we have the definition of stability. This is the definition of stability, so we can break it down a bit to make it simpler. And basically, what it says is, if we start from something that is very, very close to the equilibrium, where delta is arbitrarily small, so it's a ball centered in the equilibrium, we need to stay close to it. For an equilibrium point to be stable, we need to stay close to it. So the evolution needs to stay close to the equilibrium on another ball, which is different from this one potentially, but still it doesn't go beyond that. So we start close, we end up close. Not just we end up, but we stay close for the whole trajectory. And very simply, an equilibrium point is unstable if it's not stable. So if this does not hold, to have a visual breakdown of this definition, we can see this. So we have these two balls here that are centered in the equilibrium, and then we're saying if we start inside one of these balls, the evolution stays inside the other. So no one here is saying you have to go back to the equilibrium, which is what I said that happens, for example, for the pendulum, right? Because you swing the pendulum a tiny bit, and at some point, since there is friction, the pendulum will stop. For now, it's just saying it stays there. It stays close. It doesn't stop. It doesn't converge back to the equilibrium, even though it would be a very nice property to have. So actually, this is a very important property in control theory, which is called asymptotic stability. An equilibrium point is said to be asymptotically stable if it is stable, so the evolution stays very, very close to the equilibrium, but also this thing holds. And this thing here says if you start close enough to the equilibrium, you will converge back to it eventually. So this says that at some point the evolution will converge to the equilibrium. It will go back there. So this is, for example, what happens for the pendulum, right? Because eventually the swinging stops and the pendulum goes back in rest position, which is the equilibrium point. So asymptotic stability is a very important concept in control theory, and it's a local concept in general, defined by the basin of attraction, because there's some basin of attraction, so some area in which this condition holds. But this is the definition. It's quite an important concept, and so keep it in mind because it's basically the foundation of many of the things that we will see in the course. So now we have this concept, right? But how do we apply it? How do we know when a system is stable, asymptotically stable, unstable? Like this is, for now, this is unclear. Everything is done with linear algebra, which hopefully you have seen in previous courses, bachelor or whatever it is. But now we will give a very quick recap on some important facts of linear algebra. So we take a matrix. This matrix is conveniently called A, exactly like your dynamic matrix. And it's conveniently of shape R times n cross n, which is the size of your dynamic matrix because the state is n-dimensional in general. This square matrix has eigenvalues and eigenvectors. Eigenvalues are scalars, eigenvectors have the size of the matrix. And the relationship between eigenvalues and eigenvectors is that if you multiply the matrix by the eigenvectors, you get exactly eigenvalues times the eigenvectors. And then if you solve for u, which is the eigenvectors, you get something like this. How is this solved? What do you get out of it? Well, the first trivial solution would be u equal to 0, but this is uninteresting. The non-trivial solution, where u is different from 0, so where you actually get an eigenvector, are the ones that we're interested in. And with those, you find all the eigenvalues and their associated eigenvectors. This is done by solving the determinant of the matrix, and the eigenvectors that you find from this span a space, create a space, which is called eigenspace of the matrix. So more simply, how to find the eigenvalues, we can use the characteristic polynomial. So the determinant of this lambda I minus a is actually a polynomial, because lambda is your unknown, and you want to create lambda I, which is a diagonal matrix which has lambdas on the diagonal, and then find the determinant of lambda I minus a, and then you want to solve for 0. So we can see a very quick example of this to grasp the concept behind it, which is we have a matrix, we compute our lambda I minus a, which is lambda minus 1, because it's minus a here, then minus 5, because this lambda I, as I said, is a diagonal matrix, so it does not impact this, but a is still reversed in sign, so it is minus 5, and then lambda minus 4 here, and this stays 0. Then you compute the determinant, and you find that the determinant is equal to 0 for lambda equal to 1 and lambda equal to 4. This is expected because, if you remember, if a matrix is triangular or diagonal, the eigenvalues are actually on the main diagonal. So of course it's 1 or 4, because this matrix is triangular in fact. So triangular means that everything below or above the main diagonal is 0, which here happens because everything below the main diagonal is 0. And this holds also for diagonal matrices where everything below and above the main diagonal is equal to 0. Some quick facts of linear algebra: eigenvalues are invariant under affine transformation, and then there are two important properties, which are the algebraic and geometric multiplicity. So a number can be an eigenvalue, so can solve the characteristic polynomial, and the number of times it solves the characteristic polynomial, it's called algebraic multiplicity. On the other hand, you can compute the eigenvectors associated to this. This is not necessarily equal to the number of times this eigenvalue solves the characteristic polynomial. It could be less. This is called geometric multiplicity. So geometric multiplicity is always smaller or at most equal to the algebraic multiplicity. And then we have a last important thing, which is if an eigenvalue is complex, its conjugate is also not an eigenvalue. So you will always have them in pairs. There will not be just one. This will never be the case. How do eigenvalues relate to the stability and to what we said before? Well, it's actually pretty simple. A system is asymptotically stable if all of the eigenvalues have negative real part. We don't care whether they are real or complex conjugate. This is absolutely irrelevant for the stability. What is relevant is that the real part has to be 0, or it has to be less than 0, sorry. And a system is said to be instead marginally stable, or just stable, the very first definition of stability that I gave you, if all eigenvalues have non-positive real part. So they could be 0. Actually, this is not entirely true. They don't need, if they are 0, there's another condition that has to be satisfied, which is the multiplicities that we defined must be equal. So the eigenspace that we create must be equal to the the dimension of the eigenspace must be equal to the algebraic multiplicity of this eigenvalue. And a system is unstable if and only if there is at least one eigenvalue with positive real part. Also there's something else. It's actually the complementary case as before. So if there's one eigenvalue which has 0 real part, for which the multiplicities differ, that's also an instability case. Forgetting a bit about this multiplicity thing, basically the stability breakdown is if everything is on the left-hand plane, we have asymptotic stability. If something is on the imaginary axis, we have marginal stability. If anything is on the right-hand plane, we have instability. We can now visualize maybe a bit better an example, and I mentioned the pendulum already, so you probably have already an idea of it. Now we can actually see how this is working out for a pendulum. So we have a pendulum, length L, with a certain mass m, and with a certain damping factor m. And then we have this pendulum which evolves with a certain angle, which is the swinging angle theta. Then what happens is that this is the dynamical model. This is coming from physics, so we will not tackle it here. And the state variables that we consider are theta and theta dot. So the swinging angle and swinging velocity. Well, the state space representation, by just inverting this and substituting theta and theta dot as this, looks like this. So we have the derivative of theta is equal to theta dot, which makes sense. And the derivative of theta dot, which is theta double dot, is obtained by inverting the dynamical model. We already know that the pendulum has basically two equilibria. One is when it's pointing down and it's at rest, and one is the case which is similar to the pencil that I mentioned, where the pendulum is up, is a very unstable position, a very unstable equilibrium from the understanding we have, but it's still an equilibrium. In fact, this is the case, two equilibria, which looks like this. In one, the pendulum is going down and the theta is equal to 0. And one, the pendulum is balanced up with the theta equal to pi. And the intuition is exactly what we mentioned before in the course. So this one is asymptotically stable, because if we perturb it a tiny bit, it will swing and then stop again, while the second equilibrium is instead unstable, because small perturbation would cause it to fall down, swing a lot, and then eventually converges again to the stable equilibrium. So with the pendulum we are actually lucky, because the instability of one equilibrium makes it such that if perturbed it will converge to the other equilibrium, but still it's an unstable equilibrium. Now, we talked about stability a bit, but we haven't really tackled the differential equation that we have here. So it's a differential equation, so we don't have the explicit formula, the explicit equation for x. But what if we want to have it? What if we need to know what x looks like? So not the variation of x, which we have, but the actual x, so the actual form of x of t. Well, it turns out that the computation is not that easy, and it actually goes through all the passages for solving an ordinary differential equation. But in the end, what we end up with is something like this, that includes an exponential of a matrix and an integral with, again, an exponential of a matrix. And since x is the state and the output is defined in terms of the state, we can also find the output. Now, the explicit derivation will be given as an extra. Is not strictly part of the course, but you're invited to check it out to understand how these equations have been obtained. And then we have that all these terms here are exponential of matrices and product of matrices. Usually we give them names because it's easier, it's kind of important quantities in control theory. So we call them with some names to end up with something that looks like this. So this is the explicit solution for x and y, but it's quite difficult. What is the problem with it? The problem is we have two integrals. We have here something complex, which is something expressed in terms of t minus tau multiplied by something expressed in terms of tau. So it means there's two signals that we have to multiply from opposite directions. This is called convolution. And so the problem is, in general, integrals are hard to solve, And in this case, there's an integral of a convolution, which is even harder. So how can we get rid of this difficulty? How can we get rid of these very challenging equations? So the tool that we use is called Laplace transform. Laplace transform is a tool that transforms a real valued function to a complex valued one. So from the time domain, which we have this real domain because time is expressed in the real domain, we pass through Laplace domain, which is complex. This is the definition of the Laplace transform, which is not very important at the moment. What is important is the properties of the Laplace transforms. So the first property is linearity. This is very nice because we're dealing with a linear system. We already mentioned that we want to respect the superposition principle, that we want everything to be linear. Linear interpolation of causes lead to linear interpolation of effects. So having linearity also in this complex domain is actually very nice. Then there's another property, which is the derivative, which is also very important because let's forget a bit about this initial state. It says that the Laplace transform of a derivative is just s times the Laplace transform of the function, which is something that comes very handy because we have the derivative, the time derivative of the state, which is x dot in the main equation, in the state space representation of the system. So this actually comes very, very useful for us in our case. Well, what comes even better, even more useful, is the convolution, because the convolution of two signals under Laplace transforms turns out to be just the product of the two signals. And this is something very nice because it simplifies our explicit equation by a lot. So in this Laplace domain, also called frequency domain, what we obtain is that the state space representation becomes something like this, and then we solve for x, and we obtain something like this. Now from the state, we can, as we know, obtain the output, because we know that the output is just c times the states plus d times the input. And these are basically our explicit formulation of state and input, which is quite simple because in here there was an integral with a convolution, while in here is just like product. Matrix products, there's an inversion of a matrix, but this is all well-known operations that we know how to do and that linear algebra tells us how to do. Another important thing is that this term here is called transfer function, and it's actually very, very important because if you look at it, we have that the initial state, let's forget about it because it could be 0, and then basically the output is described as transfer function times the input. So the transfer function is something that transfers directly the input to the output. So it describes how the system evolves in terms of input and output behavior. So since it gives all the information about the input-output behavior, it should embed some information about stability. Actually it does. So the transfer function has a matrix inversion in here. So it will be a fraction which has s, which is this complex variable, both numerator and denominator. But we want to focus on the denominator. The poles of the transfer function, which is the root of the denominator, are all eigenvalues of the system. Not all the eigenvalues are poles, though, because there might be that there are cancellations in here, and so there are some eigenvalues that do not appear as poles, but all poles are eigenvalues. So we can study the transfer function and see, okay, we have an idea whether the system can be stable or not. To check whether all poles or eigenvalues appear as pole, we have to do controllability and observability tests. So basically, if an eigenvalue is both controllable and observable, then it's something that appears as a transfer function. And this kind of makes sense, like if you intuitively think about it, the transfer function is something that relates the input to the output. So the eigenvalues should be reachable from an input point of view, so they can be controlled, because the input is actually the control signal that we are injecting in the system, and they have to appear in the output. So as an external observer outside of the system, you have to notice what kind of evolution these eigenvalues lead to. So they have to be observable. So these are the concept of controllability and observability for having a pole, for having all eigenvalues appear as poles. It's two rank conditions, where you want the rank to be equal to n, where n is the dimension of the state. This line here, this vertical line here, and this horizontal line here just indicates the juxtaposition of matrices. So we have the matrix A minus lambda I, where lambda is your eigenvalue that you're testing, and then close to it you put B, the matrix B. You have this extended matrix and you check the rank. And same thing happens here, just that C goes at the bottom. So these are a lot of concepts that we've introduced so far about systems theory in general, theory of dynamical systems. And I want to close this lecture with one practical example. So one thing that gives you the grasp of what's happening. And the practical example, we've seen the maths, we've seen the pendulum, but they are not really concrete. They do not belong to the real world. So I chose the bicycle. Bicycle is a tool that more or less everyone knows. Everyone knows how it works. And we will introduce some models to understand a bit concretely, but from a math perspective, how the bicycle works. So all the models, there will not be the explicit derivation of them and everything that comes from physics, because it's outside of the scope of the course. But anyway, I will give you a PDF, a paper, and some report that explains everything, also the physics behind it, in case anyone is curious about it. So we have a bicycle. This is a bicycle we all know. Here's the two wheels. There's a certain center of mass somewhere, center of the wheels, height of the bicycle, distances between center of the wheel and the center of the bicycle, or two centers of the wheel, and one angle, which actually will be very important. This is the angle of the front fork. So when you're riding a bicycle, you have this axis that goes from the center of the wheel to your handlebar, and this is the front fork, and usually is a bit inclined, as you can see it here. It's never really vertical, right? But this defines an angle, and it's a very important thing for the bike. Also, we are assuming that the bike moves at a constant velocity v. So for now, we're not having, I don't know, steering or changing velocities, accelerations, and stuff like that. We just assume a very simple case in which the bicycle is going at certain velocity v. We also have a 3D drawing of this bicycle that highlights some angles. So the bicycle can tilt on the spot, and this is given by this angle phi. Also, the bicycle can move, you can steer the front wheel of this angle delta so that you know that you can change direction. Again, everything under the assumption the velocity stays the same. This is the only assumption we're doing. And also, if the bicycle tilts and the front wheel steers, then the front wheel will have a different tilting than the rest of the bicycle. And this different tilting, we call it phi f, phi front. Under these conditions, under these definitions, we can start inspecting the bicycle a bit better. So we start with something which is called neutral model. This neutral model is not really a real model, because actually assumes that this front fork angle is equal to 90 degrees. So this axis here is perfectly straight with respect to the horizontal plane. This is not really the case of bicycles, but it's a simplification, because the dynamical model of it will actually turn out to be way simpler thanks to this. As I said at the beginning of the example, I will not enter into the physics of it in this lecture. And so you can just trust me when I say this is the dynamical system. So this is the dynamical equation expressed in terms of the tilting acceleration. And there are some quantities such as the steering velocity, and tilting. Now, intuitively, what can be a good state and what can be a good input? Well, a good state that we want to ensure asymptotic stability of could be the tilting, because the tilting ideally goes back to zero eventually. So we want actually the asymptotic stability. So that means we're not falling, we're not oscillating all the way on the bicycle, but eventually, even if there is some oscillation at the beginning, then eventually the bike stays up and doesn't fall down. So it's a good state candidate. A good input candidate is the only thing we can do. We can grab the handlebar and steer. So delta could be, for example, a good candidate for the input. This is exactly what happens. So one state is phi, the tilting. One other state is something more complex, not just phi dot. So the reason is that this simplifies computations. In theory, the state could be whatever you want, but then you have to deal with computed transfer function, computing the state space representation, which can be then arbitrarily complex. So I chose this state, and in the PDF that I will provide you, there's actually explained explicitly why this state is better. And the input is delta. So we have our state space representation. From the state space representation, we need to compute the transfer function. So you can do the computation because now you have the formula for the transfer function. So you have to multiply C and invert S I minus A and then multiply by B and everything. We here don't have any interaction between, any direct interaction between input and output. So there's no D. So that part you can skip in the formula. And the transfer function turns out to be something like this. Now at the first glance, this transfer function is actually quite problematic. So most of the things are constants. A, V, B, H, and G, they're just parameters, so we don't care about them. But the thing is that this transfer function has two poles, because we have to put S squared minus GH equal to 0. And the poles of this, so the solution of this, will be something like square root of GH and minus square root of GH. And this is a big problem because square root of G over H is a positive number. G is the gravity acceleration, H is the height of the bike, so it's something positive. So the square root of something positive stays positive. And this means that this model is unstable. And this is weird. So it says that the bicycle is unstable no matter what. So basically, this model is unstable. If you do the check, it's actually stabilizable. So it means that there is a steering that you can do in order to not fall down. But then intuitively, what it's saying to you, that basically you cannot ride the bicycle without holding the handlebar and without falling down. So in this case, math is forcing you to fall down when you leave the handlebar, which if you ride a bicycle, if you've ever ridden a bicycle before, is not the case. If you go fast, you can actually leave the handlebar and the bicycle actually goes forward, doesn't fall. So this model doesn't explain this. And this is actually because of the front fork of this angle that we set equal to 90 degrees. So if we do the actual model of a bicycle with the inclined front fork, so lambda is not 90 degrees, it's a bit less. So C is not 0, because that's the direct consequence of having lambda equal to 90 degrees. We have another model. Problem with this model is that it's fairly complicated. There are many things going on. All the symbols are just numbers. They're just basically construction numbers. There's the momentum of something, there's the height and everything in there. So we don't really care about all these numbers here. Again, you will find all the explanation of it and all the derivation of this on this PDF that I'm going to provide you. But this can just be rewritten as this. Just a bunch of numbers here. Whatever they are, we don't care. And these are the torque. This is the torque and the variation of torque that one applies on the handlebar. So what happens is that a good state candidate is still the tilting, because it's still the thing that we want to stabilize. A good input candidate is the torque, because the torque that we actually apply on the on the handlebar. The transfer function is huge because you've seen the physics equation, so you can imagine a transfer function is huge, but you can try it out. What happens is that you compute the transfer function, you compute the poles, and again, everything will be present in this PDF, and you find that all poles have strictly negative real part when this happens. So when the velocity is bigger than a certain number, a certain positive number. And this is what we expect, because the system will be asymptotically stable, so you will not fall down when the velocity is high enough. This is called self-alignment velocity, which actually self-aligns the bicycle. And it means that you will not fall down without applying any torque, without putting your hand on the handlebar. So you can ride a bicycle without hands if you go fast. I can introduce now another model just to give you a very light idea of what's going to happen. Because at the moment we are considering the bicycle and there's nothing else. The rider, for example, the person on top of the bicycle was never considered in this. But actually the rider can have a very important effect on the bicycle. Because when you're on a bicycle and the bicycle tilts, you can decide whether with your body you want to tilt more or you want to tilt in the opposite direction. So you are somehow introducing a new angle, which is not strictly part of the bike. It's an angle, which we call with this other phi here, which is completely independent on the angle of the bicycle. It just goes on its own. Well, I will not give you here the model, or I will not tell you exactly what happens here, but the intuition is that the rider introduces another control variable. It's another input. There's not the torque anymore, or the steering, whatever you're using, depends on the model you're using, but there's also this other control variable. And since we have more inputs, then it means that the system is intuitively easier to control. Not everything relies on the torque, but the effort can be shared between the torque and the angle. So this is more on a control perspective, so it's somehow a teaser of our next lecture, which will be more focused on control rather than just theory of dynamical systems. And we will actually take this bicycle example and elaborate it a bit and try to introduce controllers for it. And I will show you a few things and a few interesting control strategies and control mechanisms for the bike. So as a recap, in this lecture, we had an introduction of control engineering. First was a lot of nomenclature about what is a system, what is evolution, dynamical systems, and all that. Then we had the model. We introduced all the properties that we're interested in. We analyzed the linear system from a stability point of view, but also about the explicit representation of it. And then we introduced the Laplace domain, the frequency domain, and in the end, we closed with an example. So I used a bunch of references for preparing this lecture and preparing these slides, and I invite you to check them out, but you can actually check out any book or any presentation that's been around, because this concept is something that has been around for now many years. So you find plenty of very high quality material that explains these concepts. So I really invite you to check it out and go in deep to understand better or to get more details if you want. The last reference is this paper on bicycle dynamics and control that I used for the bicycle example. This is what I will give you together with another report that I did with some colleagues that explains actually the physics behind it, so you have an even more complete understanding of what happens with these bicycle models. So I will see you in the next lecture on control theory, and thank you for your attention.